That's a good question. We're starting about page 205, somewhere around there, 200. We're going to be looking at representing numbers graphically. And we've already done a little bit of this when we talked a little bit about working with negative numbers. We talked about number lines. And there's actually a couple of different representations of numbers we talked about there. We talked about vectors for adding negative numbers, like 4 is just an arrow that starts at 0 and goes to 4. That's the vector for 4. Or we might have -3 starts at 0 and goes to -3. That's the representation of -3. And when we do operations with negative numbers, with integers, these vectors are really the key to doing those operations. Well, that's a working representation. If we just want to represent the value and not be able to do anything with it, we could represent 4 with just a dot at the number 4 on the number line. And we could represent -3 with just a dot at the -3 on the number line. Well, many times when we're working with numbers, we have numbers that go together. And often we want to be able to demonstrate, show those two numbers and their relationship with each other. So we might have two numbers like 5 and 3 that go together. Well, first of all, this thing here is called an ordered pair. Pair, obviously, because there are two numbers. Ordered because the order does matter. The first one, the one that's in the first position, represents one thing, and the one that's in the second position represents a different value. To graph these, to represent them graphically, visually, like we do with the number line, we could do a number line and try to graph 1, 2, 3, 4, 5. I could put dots at 5 and 3 and then somehow link them with an arrow showing that the 5 comes first or whatever. But that gets very messy and very clumsy. In fact, they searched for a long time for a way to represent those pairs of numbers together. There's actually a man by the name of René Descartes that came up with the Cartesian graphing system. And what he did was he said, let's take that standard number line pretend these are evenly spaced. And we're going to use that to represent one of those numbers. That's going to be the first number, and we're going to call that the independent axis. The reason for that is when we graph these, the two variables, usually the first variable is considered the independent variable because it's the one we can change or that changes on its own. The second variable is considered dependent because it usually changes as being influenced by the first one. Now, many of you have probably heard this referred to as the x-axis because x is the variable that is most commonly put on that axis. And then what Descartes did was said, well, to represent the second number, let's take a second number line and let's run it vertically, perpendicular, and number, just like we would before, positive numbers going up now and negative numbers going down. And that, of course, is referred to as the dependent axis. Again, many of you may have referred to that as the y-axis. And as I said, this axis is the one that usually is being influenced, whatever variable goes here is being influenced by the value on that horizontal or independent axis. So if I wanted to graph that pair, 5, 3, I would go to the horizontal axis. This first number is always the independent or the x variable, the horizontal variable. That's 5 on that axis right there. The 3 then is on the dependent axis. 3 is right there. Well, to graph those two numbers together, we project them out into space, and we put one point right there. That point is the point 5, 3. Because if we trace it down, its shadow falls at 5 on the x-axis, and if we trace it over to the left, its shadow falls on 3 on that vertical or dependent axis. Let's just try a couple of examples here. What would be the coordinate of that point there, the ordered pair for that point? -7, 4. Good. How about this one? -2, -4. Good. That independent axis, so the horizontal axis, always comes first. Also, one way to remember, x, if you're calling them x and y, x comes first alphabetically, so that comes first in our ordered pair. So why is it important to be able to graph numbers like this? Well, because in nature, there are a lot of relationships where one variable, I want to be careful not to say cause and effect, because it's not necessarily cause and effect. But as one variable changes, the other variable tends to change as well. For example, we might have height and weight. As a general rule, as you get taller, you tend to get heavier. So we have our axes here for the graph, and you'll notice I'm only using this section over here. I'm not sure if I want to know what that's about. We only have this section where both of the variables are positive because it's not possible to have a negative height. And as much as we'd like to, it's not possible to have a negative weight. By the way, in our overall graph, that is what's referred to as the first quadrant, or quadrant 1. As you go around, this over here is actually called the second quadrant, third, and fourth. So we still have our independent and dependent axes, but we're only using just the first quadrant of our graph. So what's going down here on this horizontal axis is going to be the height. The reason for that is, like I said, I don't want to say cause and effect, but the height, changing your height usually does influence your weight. As you get taller, you do tend to weigh more. The opposite is not necessarily true. You can put on weight, it's not going to make you taller. Trust me, I've tried in the last few years. So the weight doesn't necessarily influence the height. It's the height, it's the weight that's influenced by the height, not the other way around. So the weight's going to go here. That is the dependent variable. It is the one that is changed by changing the height. So then we can gather data. Let's say we're going to do our height in inches just to make it easier on me here. So let's say we have somebody who is 68 inches tall and weighs 145 pounds. I'm only going to put a few people in here. Let's say we have another one that's 71 inches tall and weighs 205 pounds. 70 inches tall and 230 pounds, and 67 inches tall and 150 pounds. First thing we have to do is we have to set out our graph here so that these numbers are on there. We have to include numbers for the height that go as small as 67 and as large as 71. It is okay to start at something other than 0 here. I can do that on my axis, which tells people that This axis is broken, it's not continuous. So this is 67, 68, 69, 70, 71, and that's as far as we need to go. Going up the side here, I'll probably end up doing the same thing because what's the smallest number I need on there? 145. So I might start with like 140, 50, 60, 70, 80, 90, 200, 210, 220. And I'm a little short here. 230 is going to have to be up there. And then I just put points on here. 68 and 145. Well, here's 68. 145 is right about there. 71 and 205. Here's 71. 205 is going to be right about there. 70 and 230. Here's the 70 right up through here. 230 somewhere in here. So right about there. And then 67 and 150. Here's 67. 150 is right about there. So I have these points on the graph. Now, right now, there's not enough points on here to get much of a picture. If I added more points, measured more people, in other words, let's say we have somebody who's 69 inches tall and about 175 pounds. Well, their point would go, here's 69, 175, somewhere in there. I might have another person who's 70 inches tall and 180 pounds. 70, 180, somewhere like that. And as I put more points, I'm not going to keep listing them out in my table, but as I get more points on here for people, there should evolve or should develop a pattern for those points. If you look at it, you can almost imagine that as you move from left to right, as the height gets larger, the weight gets larger. Now, it's not perfect. You can see there's points out here. There may end up being points way down here, somebody who's really thin. But in general, as I said, as the height gets larger, the weight gets larger. And that is what we refer to as a trend on our graph. In this unit, in this course, actually, we're not going to get into finding the equation of trend lines. But that would be one of the next steps that you would continue on to. That would be a big part of a full-blown statistics course in our next unit if we had time to go that far. We're coming up with an equation to describe this data. The closer those points lie to a straight line, like those points there are almost exactly on a straight line, it's what we refer to as a stronger relationship. The technical term they use for it is called correlation. I don't know if I spelled that right or not, but you guys get the picture. Correlation is how tight that relationship is between the variables. This red line here would be, those purple dots would be a very strong linear correlation. This is what we would refer to as a positive relationship. It's positive because as the height got bigger, the weight got bigger. You could have dots like we did in our graph, like that still, they definitely show a relationship, but if I tried to draw a line through them, they're not all on the line. That's a little bit of a weaker relationship or weaker correlation. And actually this here would probably be a moderate correlation. because they show the trend, but they're not all really close to that graph, that line. And then, of course, we could have points like this. Pretend those look like dots. I'm getting a little sloppy here. Where there's really no way, no matter what line I draw through there, it really doesn't fit the data. This would be said to have no correlation or no relationship. So what that's saying is, as the value of this independent variable changes, it has no effect on the value of that dependent variable. Here, it's saying it does have an effect on it, but it doesn't totally determine it. Kind of in terms of our height and weight, as the height gets larger, the weight tends to get larger, but there are other factors that might change it too. Now we can have other strong or moderate relationships that might look like this. These, again, are close to the line, but not right on it. That would probably be a moderate relationship again. The difference is here that those points, as the independent variable gets larger, the dependent variable gets smaller. That's what we would call a negative relationship or negative correlation. As we go on with this unit, next week, actually, we'll talk about direct and inverse relationships. And direct relationships are positive correlations like this one. Inverse relationships are negative relationships. Both of them are very important. So let's look at now more of the mathematical side. We've looked at equations like 11 equals 2x plus 3. And what did we do to solve that equation? Subtract 3, good. So 8 equals 2x, and then divide by 2. So 4 equals x. Well, there's an equation that's related to that, very similar to that, that might look like this. 7 equals 2x plus 3. You can see it's the same equation with just a different number over here. The steps to solve it will be exactly the same. We would subtract 3 and divide by 2. In this case, of course, 2 equals x. And we can keep going. There are literally an infinite number of equations that could be solved by doing those exact same steps. Subtracting 3 and dividing by 2. It's what we call a family of equations. And the way we represent that family of equations is like this. Instead of having a number up front here, it's y equals 2x plus 3. To represent the solutions to an equation like this, because there are an infinite number of them, any value we can think of for x, there's going to be a value for y. And the other way around, any value we can think of for y, there will be a value for x. There are some equations that have limitations, but not this one. So the only way we can really represent that solution is with a graph. To start out, to create the graph, we're going to start out with a table here at first. So what we're going to do is we're going to pick values for x, and we're going to figure out what the value for y has to be. Notice my table's a little lopsided here, so I'm making room to do some work in the table. Okay, so now to graph this, and on my scale got a little off on my axes of my graph over there, but it'll work. We have to pick, we're going to just pick values for x and figure out what y has to be. To make this work best, we pick values that are kind of scattered across the graph. Some that are over here in the negative, some that are in the middle, and some that are in the positive. To make it simple on myself, I'm going to pick -2, -1, 0, 1, and 2. Just to see what that does. Now that might not be enough to figure out the shape, or it might be. If we get those on the graph and we can see what the graph looks like, we can go ahead and draw it in. If not, we'll pick more points and keep going until we can figure out what it looks like. So if x is -2, y has to be 2 times x plus 3. So that would be 2 times -2 plus 3. Well, what is 2 times -2? -4. There we go. -4 plus 3 is -1. So what that gives us is the ordered pair. When x is -2, y is -1. On the graph, x is -2, y is -1. It's right there. I didn't get that real close, did I? Right there. It's better. If x is -1, y is 2 times -1 plus 3. So again, 2 times -1 is -2, plus 3 is +1. Yes. So that gives us the ordered pair that when x is -1, y is +1. So over here, x is -1, y is +1 is a dot right there. So now, when x is 0, it's 2 times 0 plus 3. Well, 2 times 0 is 0 plus 3 is 3. So that gives us that ordered pair. X is 0, y is 3. 0, 3 is right there. So then when x is 1, 2 times 1 plus 3 is 5. Very good. So we get the ordered pair. When x is 1, y is 5. Right there. And then we have, finally, when x is 2, y is 2 times 2 plus 3, which is 7. There we go. 2, 7. It always is a little bit of a shock when we get back to the negatives again. So at 2 and 7. Now we'll notice if I had drawn my graph real well, it is a straight line on a graph. Not everything we graph will be a line. Of course not, right? I'm not sure what you're insinuating by that. X squared plus 2x minus 3. So again, I'm going to make a table. I want to pick values for x and figure out what y has to be. So I'm going to start out with -2 again for x. Now, I didn't write in my other numbers because this might take a little space to do the rest of this. So then y is x squared, which is going to be -2 squared, plus 2 times x will be 2 times -2 minus 3. So this might take a little work. What is -2 squared? Positive 4. Now be very careful with this. You're going to just punch these in your calculator. I do negative 2 squared plus 2 times negative 2 minus 3. It gives me negative 11. Is that the correct answer? Well, the calculator said so. It's got to be correct, right? A couple of you said no. What's wrong with that? Well, it's the negative 2 squared. It's trying to tell me that's negative 4. What's happening there is on a calculator, it does order of operations exactly. The power of 2 comes before a negative. So what it's doing is it's squaring the 2 and then putting the negative in front of it. So on the calculator, when you square that negative 2, you have to use parentheses on most calculators. So be careful with that. So if we were punching this in, the safest bet when you're punching in something like this on your calculator is anywhere there's a negative to put in the parentheses, just like I wrote it there. So parentheses negative 2 squared plus 2 times parentheses negative 2 and minus 3. It gives you negative 3. And yes, 2 times negative 2 would have been a negative 4, and then minus 3. 4 plus negative 4 is 0, minus 3 is negative 3. So that gives us the ordered pair when x is negative 2, y is negative 3. So x is negative 2, y is negative 3 is right there. What's that? Okay. So let's try negative 1 for x. So it's going to be negative 1 squared plus 2 times negative 1 minus 3. Negative 1 squared is 1. 2 times negative 1 is negative 2. Minus 3, I get negative 4 there. You guys can double check me. No? Totally believe me? So when x is negative 1, y is negative 4. So negative 1, negative 4. It looks like it is going to be a negative relationship. Good point. If it's a line, it's sloping downwards, isn't it? It is slanting downward. Well, how about when we let x equal 0? This is 0 squared plus 2 times 0 minus 3. Well, 0 squared is 0. 2 times 0 is 0. Minus 3 is negative 3. So we have the point when x is 0, y is negative 3. 0, negative 3 is there. Well, we now know it's not going to be a line, don't we? So let's keep going. Let's try x equals 1. So 1 squared, 2 times 1 minus 3. You guys tell me what you get. 0, perfect. When x is 1, y is 0. That's right here. Right now, it's really tough to tell what shape this is taking on the graph. I would probably keep going and put x equals 2 in here to see what I get. So 2 squared plus 2 times 2 minus 3. See what you come up with. Yep. So you get 5, right? So we've got x equals 2, y equals 5. So that's a point somewhere in here, 2, 5, right there. I've got a pretty good idea what's happening over here right now, something like that, right? I'm not totally sure what's going on over here, so let's take some points like x equals negative 3, x equals negative 4, and see what we get for y. Let's start out with x equals negative 3 and see what happens. So x equals negative 3, we've got negative 3 squared plus 2 times negative 3 minus 3. Anybody get a result yet? Zero. Yes, so when x is negative 3, y is 0. So here, x is -3, y is 0. You're noticing some symmetry here, I'm guessing. Yes, it's going to look like that. This is what we refer to as a parabola. It makes that shape because, of course, it's an x squared in there. This strategy here, but you notice what I did is I started out by picking some points for x, and I got my first several points on the graph. These few here. And then from there, I decided, yeah, I want one more. So I took the x equals 2. Then I decided I need more points over here. So I took the x equals -3. Graphing isn't an exact science. You can't just pick points, plot them, and draw the graph. You do have do what we just did. Pick some points, plot them, and then maybe pick some more to see where you have to fill it in. Now I posted a worksheet on Blackboard. If you had time, if you got to print it off, that is wonderful. If not, I'm going to put it up here for us quick. Maybe. And this worksheet has a bunch of equations on it that basically I started the table. I gave you some values for x to try, but you may find that some of those values don't help. Some of them you may need to use more. You may want to cross off some of them, use different ones. Some of them you may want to try more points. And for the first one here, y equals 3x. Oops. This computer's been acting goofy all day. One more. Y equals 3x minus 2. So if x was -2, y is 3 times -2 minus 2, which is going to end up being -8. You got it. So -2, -8 is that point on the graph. Plot those points. What I'd like you to do is, and you can work together if you want to. We have about 15 minutes left here in the first hour of class. I want you to take those 15 minutes and I want you to work on plotting these points and tables and graphing some of these. Skip around. I recommend that you do 1, 3, 4 is okay. Do like number 6 and 7. Number 8 is a fun one to try. So maybe do those first. If you get time, go back to the other ones. I will leave this up here for anybody that didn't get their sheet printed off. If you want to copy down the first couple equations and work on them, if you need me to scroll down for you, let me know. Sure. 1, 3, 6, 7, and 8. What's that? Okay. Are you getting the axes mixed up? Or yeah, because -2 here is going to go this way. This is the -2, and then -8 goes down that way. X goes side to side, Y goes up and down. Should be -5. So if you did 3 times -1 minus 2. Okay. Okay. Perfect. We'll pause this and we'll let you guys see if you're going on track here. The first one should look like that. Perfect. So just a little bit of a progress check here. Number 3. What do we have? -2, 1. -1, 0. What does it do? Look something like this. Does that look familiar? No? Here, hopefully. So I want to just look at some of the graphs here. So I'm going to go back up here and I'm going to do all of them. And if you didn't get time to do them, that's fine. You can sketch them in or sketch them off to the side and fill them in later. Number 2 here should look something like this. So number 2 is a line as well, just like number 1. Number 3 we sketched in there. Number 4 is going to look something like that. Now notice on number 4, I put an arrow on one end but not the other. All the other graphs I've put an arrow on both ends. The reason for that is on number 4, if x is -6, -6 plus 6 is 0, and the square root of 0 is 0. That works fine. But if x were -7, what's -7 plus 6? -1. And what's the square root of -1? Your calculator would give you an error, wouldn't it? You can't take the square root of a negative number. So x cannot be any smaller than -6 because we can't take the square root of a negative. Number 5, again, most of you probably didn't get time to do that, so you can sketch it in off to the side or whatever you want to. Should look something like this. It is a line again. Number 6. There's going to be a nice, neat little curve like that. Oops, number 5 disappeared on me. There. Number 7. Should look something like that. Got a nice little S-type curve. Wow. Computer's got a little attitude today. There. Number 8 is the one that drives people nuts. Number 8 should look something like this. It's actually 2 separate curves. Similar to number 4 where we had that square root where we couldn't have any values that are negative. Here, if I put x equals 0 in here, what would be 8 divided by 0? If you tried it on your calculator, it's going to say error. It's going to say you can't do it. Say division by 0 error or just error. You can't divide by 0. So x cannot equal 0 here. That's what we refer to, and you don't need to know this term, but it's called an asymptote. It's a value on the graph that one of the variables can't equal, so it has to skip over that value. Number 9. Again, like I said, most of you didn't get here, but that is a really skinny, narrow one of those parabola things that we were looking at. And number 10 is another line. So as we look through these, we see that number 10 was a line. Number 5 made a line. And numbers 1 and 2 made lines. So the question I ask you is this. So we said numbers 1, 2, 5, and 10 made lines. The ones that were not lines were 3, 4, 6, 7, 8, and 9. I want you to look at the equations for those graphs and tell me what's different about them. More specifically, what do these ones that are not lines have in their equations that are not in the ones that do make lines? If you look at number 3, what's different there that sticks out right away on number 3? X squared. How about tie that in with, what is it, number 7? X cubed. There's a power on the variable. If you remember when we talked about order of operations, powers and roots work together. So that would also include number 4, where you have a square root. So that's one thing that makes them not lines, if there's a power on the variable. What's another thing, if you look at those equations, that's different about some of them that make them not lines? Well, they don't make a straight line on the graph, definitely. Well, there's adding on like number 5 too. How about number 6? What's going on there? It's not a power on the variable, it's the variable is the power, isn't it? X is the power. The variable is in the power. That's what we call an exponential equation, by the way. We won't really do much with those in this class. If you went on to a 4-year degree, you would have to take an intermediate algebra class, and you would talk about exponential equations. There's one more thing. Look at number 8. What happened there? Not just in the fraction, but where in the fraction? The denominator of the fraction. It's in the bottom of a fraction, or we're dividing by the variable. These things here, we're going to call the 3 don'ts of linear equations. Those are the 3 things that linear equations don't have. So if we look at an equation and it has one of those 3 things, we know it's not going to be a line. For example, y equals 7x minus 19, is that going to be a line? Yes, it does not have any of those things. Y equals x plus 3 squared, is that going to be a line? You want to say no because there's squared there. Yeah, the square is not on the variable. 3 squared is just 9. That's technically just y equals x plus 9. That is fine. That's going to be a line. Y equals 7 plus 3x squared. How about that one? Why not? X squared. The squared is with the variable. Y equals 5 to the power of x plus 3. Why not? 5 to the power of x. X is in the power in that one. Y equals 7x minus 3 plus 5x. That will be a line because there's no powers and no dividing by variables there. No powers on the variables, no variables in the powers, and no dividing by the variables. So y equals 19 plus x divided by 7. That'll be okay. We're dividing by 7, not by x. How about this one? No, why not? Dividing by x. Good. So, as you notice, as I was going through that worksheet, I do not have the solution sitting in front of me. I was able to look at the equations and sketch out the graph very quickly. So obviously there are some patterns that are followed here. The first step is knowing what shape that graph is. And we just figured that out here. If we know that that graph is going to make a line, it's going to be a linear equation, there are only so many things that that graph can do. So we're going to focus in on linear equations. That's going to be the focus of what we're going to do mostly in this class. I'm going to drop down here. So I'll put a graph over here, and I'm going to start out with probably the most basic linear equation I can think of. Y equals x. No powers, no dividing by variables. That's going to be a perfect little linear equation. Well, for that one, if x is -3, what's y? -3. So 1, 2, 3, 1, 2, 3, right there. If x is 0, what's y? 0, right there. How about if x is 2, what's y? 2. 1, 2, 1, 2, right there. You can see that makes a nice little line going corner to corner, a 45-degree angle across our graph. Just do 2 numbers. I usually do a 3rd number just to be safe, to make sure I didn't like screw something up. But you're right, 2 numbers is really all you need. Now, if you remember back when we talked about solving equations, all regular equations started out as a variable equals a number, and they were built up from there. And we built them up using our basic operations: add, subtract, multiply, divide. Powers came in there and roots at some point. Here, we can't use the powers and roots or it wouldn't be linear, but we can use the other operations: add, subtract, multiply, and divide. So let's make this more complicated by building on to it. Let's do something like y equals x plus 3. So now, if x is -3, what's y? What's -3 plus 3? 0. So -3, 0 is right there. If x is 0, what's y? +3. So 0, +3 is going to be up here. If x is 2, what's y? 5. So +5 is going to be way up here somewhere. So you can see we get that same line. It's parallel to the original line. How has it changed? It's moved up how far? 3 spots. Perfect. Based on that, what do you think y equals x minus 2 is going to look like? It's going to move down 2 spots and be parallel yet. Bless you. Let's double check it, see if that works. If x were, well, let's just stick with -3. What's -3 minus 2? -5. -3, -5, that looks right. How about if x were 0? -2, that is definitely correct. If x were 2, 0, and that is correct. So that looks right. So adding or subtracting to the x just moves the graph up or down. Well, adding or subtracting, what are some other things we can do? Multiply or divide. So let's do this. Y equals 3x. Now, if x equals, I'm going to keep this a little simpler. What if x equals -1? What's y have to be? -3. So -1, -3 is going to be right about there. If x is 0, what's y have to be? 0. We're back to going through the center again. That center of the graph, by the way, is called the origin. So we're back to going through the origin, the middle. What if x is 1? Y would be +3. That'd be right here. So we're back to going through the center of the graph. The line is now just steeper. How do you think I would make it shallower, less steep? Divide, like y equals x divided by 2. Now I'm going to rewrite that. We learned when we did fractions that dividing is the same as multiplying by reciprocal. So we're used to seeing it, instead of y equals x divided by 2, we're used to seeing it as y equals 1/2 times x. Does the same thing, okay? So now I'm going to have to do it up here. Let's see, if x is -2, what would y be? -1. -2, -1. If x is 0, 0. If x is 2, 1. So we can see here, it does. It makes that line that's not as steep. It's shallower across there. You will notice all of these lines, as I go left to right, they go up. They're positive relationships. They're increasing. How would I make it go down? There we go. Y equals a -2x. If I look at that, if x is -1, y would be a +2. X is 0, y would be 0. If x is 2, y would be -4 down here. You can see that slopes down. That's why we called this a negative relationship, is because it's a negative number multiplying x. So there's only two things that can possibly happen to these graphs. The number that's added or subtracted means instead of going through the center, it moves down. So the fact that this is -1 means we go down 1 and the graph starts there instead of starting at the center, at the origin. The 3 means it's steeper than normal. Something like that. Well, this number here that's added or subtracted is called the y-intercept. That's a fancy word for a simple concept. This is the y-axis. That -1 is where it intercepts or crosses the y-axis. In other words, its starting point is at -1 on the y-axis. The 3, oops, go ahead. Y-axis, yep, that's it. The 3, the number that multiplies our x, is called a slope. And we're going to have to take a little bit of time here to talk about slope. Slope is defined as a rise over a run. Now you might look at that 3 and think, well, there's no fraction there. Well, 3 can be thought of as 3 over 1. So what that means is we have to have a starting point, which conveniently we have at -1, right? There's our starting point. From there, we're going to rise 1, 2, 3, and run 1. That gives us a second point. So let's take a look at this. Let's say we have y equals 2x plus 3. What that's telling us is we're going to start at 3. So from 0, we count up 1, 2, 3. That is our first point of our line. To find the second point, now as you said earlier, we only need 2 points to draw a line. To find our second point, we're going to use the slope. The 2, we're going to make it 2 over 1. So how far do we rise? 2. So from this starting point, we rise 1, 2, and we run 1 right there. That's our second point. So our line goes through those 2 points. We might have y equals 1/2 x minus 5. Where's this going to start? -5. Good. 1, 2, 3, 4, 5 down right there. -5. From there, our slope is the 1/2, so we're going to rise 1 and run 2. So there's our second point. Our line goes through those 2 points. So let's throw a negative slope in there. Y equals -2/3 x plus 1. And now I put the negative up on the 2, but the negative could be up front. It could be -2/3 like that. Either way, the plus or negative always goes with the rise. The run always goes left to right, no matter what. So here, where does this equation start? Where does this graph start? Positive 1, right there. From there, we use the slope to get the second point, so we're going to rise -2. So down 2, and then run 1, 2, 3. Perfect. Notice a negative slope is a negative relationship. Yep. Only the rise, yes. If you think about it, if you look at negative fractions, like a -1/2, you can either have the negative up front, or you could have a -1/2, or you could have 1 over -2. All of those are going to equal -1/2. You could not have -1 over -2, because a negative divided by negative is a positive. So that doesn't work. So you could, for some reason, maybe you're at the very top of the graph or whatever, if you wanted to, you could have done rise 2 and run -3. Notice that puts us on the same line. But either way, but only one of them can be negative. Yes. I just always tell people, always put the negative with the rise, just because there's less confusion that way. So now this purple one here, where are we going to start? At -1. And from there, we're going to go. Yeah, we treat it as a -3/1. Yep. And we're going to rise -3. So down 1, 2, 3, and run 1. So right there's our second point. Yep, because a whole number like 5 is really 5 over 1 as a fraction. So I'm going to have you guys try to graph a couple in your notes quick. Y equals 3/4 x minus 2, and y equals -2x plus 3. We'll talk about them in just a half a minute or so here. You always start at the center, right? But the -2 means we go down -2. That's where we start. So the top one here, where are we going to start? At -2. Very good. That number that's added or subtracted. From there, where do we go? Up 3 over 4 to the right. Very good. Yeah. Remember, if it's negative, either the rise can become negative or the run can become negative, but not both. So with like up here, where this was a -2/3, we could go from that 1, we could go down 2 and over 3, or we could go up 2 and back 3. Either way, it works out. But if it's a positive slope, it's always positive run. The second one, where does this one start? +3, and then from there, down 2 over 1. Very good. And there is that graph. Now, what if we do something like that? Where does that one start? Yes, even though it's backwards, the -2 is still multiplying the x. That's going to be the slope. This is a +3 here. We start at +3. Now the negative 1/2 then is down 1 over 2. Very good. There's our line. Unfortunately, it doesn't stay this simple. What's different about this equation from all the others we've seen so far? Yeah. Y is not by itself, is it? Plus 2. Well, we have to get y by itself. Yes. Well, y is plus 2, so we are going to subtract 2. A little side note here before we finish that. When we add or subtract, you only have to do that to one digit on each side. By digit, y would be a digit, the plus 2 is a digit, 3/2 x is a digit all by itself, and the plus 3. So subtracting 2 over here gets rid of that plus 2. Where do I subtract 2 on the other side? From the 3, because that's the only thing with the same name, right? The only thing that's ones. So 3 minus 2 is 1, and I still have the 3/2 x. So when I go to graph that, you're exactly right. We start at positive 1, and from there you go what? Up 3 and over 2. There you go. There's trends. You follow trends. I will show you. It's going to take me a while to get there, but I'll show you some examples. Now here, what's going on for us? The y is not alone again. It's being multiplied by 3. To get rid of it, we're going to have to divide by 3. Now, just like we said with our addition and subtraction, let's make a note about multiplying and dividing. When we multiply or divide an equation, we have to do it to every digit on both sides. So I'm dividing by 3 here. I have to divide this by 3, and I have to divide that by 3. So here that cancels out the 3, and we're left with just y. 2x divided by 3 is just, simple way to do it, 2 divided by 3 is 2/3 x. Just turn it into a fraction. Negative 3 divided by 3, negative 1. So this starts at negative 1, and from there we go up 2 over 3. Very good. Yep, this will be 2 over 4. Yeah. No. You can reduce it to 1 over 2 if you wanted to, but 2 over 4 does the same. If I go up 2 and over 4, it's the same as going up 2 or up 1 over 2. I'm on the same line. Next step. Of course, we see here, there's a couple of things that are going to need to be done. Y is not by itself again. Think about solving an equation. Y has been multiplied by 2 and 5 has been subtracted. What do we get rid of first? Add the 5. Very good. When we add or subtract, we only have to do it to one piece. So we subtract that, it's 2y over there. On the other side, we have to add 5 to the -3. So the 3x doesn't change. That becomes +2. Then what? Then we can divide by 2. But when we divide, we have to do it to every piece. Perfect. The 2 cancels out there, leaving us with y. 3x divided by 2, well, we just make the 3/2 a fraction. 2 divided by 2 is 1. So we start at 1 and we go up 3/2. You okay? You're not the only one. Now, of course, this one, we've gone one step further. X is over there with the y. Doesn't matter. We still just need to get y by itself. We have to get rid of the 3x. We're going to subtract it. So that leaves us with 2y here. What is 6 minus 3x? 6 minus 3x. Very good. Then we have to divide by 2. And remember, we divide every piece by 2. So 2y divided by 2 is just y. 6 divided by 2? 3. -3x divided by 2. -3/2x. So we start at +3, and from down 3/2. There we go. Yeah. Yep. This is still a positive. That's where we start at. A lot of little details, yeah. Okay, so need a cheeseburger? Sorry. So you asked, where does this come into play? Well, give me a couple seconds here to develop up to that. If I have a line like this, to write its equation, y is going to equal something times x and then plus or minus something else, right? Well, this part here is the easy part to find. What's that going to be for this line? It crosses that axis at +2, so it's going to be +2. This part, the slope, is the tougher part to find. We have to have a rise and a run. And to do that, we have to find 2 points on the graph. That's why I went through both axes like this. As we move left to right, we're going to rise how much to get up to here? 2. And we're going to run 3. So that is a +2/3. So y equals 2/3 x plus 2 is what that comes out to be. Yes, you're always solving for y. Yep. That didn't look very nice. Let's try that again. So if we look at this, our intercept is where? +1, so that'll be a +1. And then we've got this point to this point, we're going down 1, -1/3. So that's a -1/3. Yeah. So I'll have you in your notes, find the equation for this one. So what's the y-intercept? -3. So it's going to be -3. And then we've got 2 points here and here. We rise how far? 1, 2, 3. And we run 2. 3/2. That's where it's kind of confusing, because if you're just graphing a point, if I'm just graphing 5, 2, I start with the x and then I do the y, right? But if I'm doing slope, it's the y first and then the x if I'm graphing a line. So it's backwards. If we're doing a point, x comes first. If you're doing a line, the y comes first. So it is very confusing there. No, we did. Well, we haven't talked about it together yet. That's why I pointed it out now. This is the x and this is the y. Yeah. So, why would this be important to you? Starts. I was making up my own language now. An IV bag starts with 2,000 milliliters of fluid and drains, I know it's a bad term, at a rate of 500 milliliters every 2 hours. Where are we going to start here on the y-axis? 2,000, right? That y-intercept, that's exactly what you said. That y-intercept is the starting point. And then our slope is a rate of change. It goes down by 500 milliliters every 2 hours. So at 2 hours, we've gone down 500 milliliters. So that's going to be at 1,500. Then at 4 hours, we're going to be at 1,000. At 6 hours, at 500. And then finally empty at 8 hours. If I draw my graph well, that would make a line. There's a good reason why I'm a math teacher, not an art teacher. Now you might be looking at it, okay, why would I ever want to graph that out? Well, let's say a bag started 3 hours ago. Has, let's see here, 850 milliliters in it. You check again in 2 more hours, and it has 750 milliliters. How long before it is empty? When you check it, there's no fluid in it. Now, you may not actually draw out a graph to solve this problem, but the thought process is the graphing thought process. You're starting 1, 2, 3 hours is where you started. 5 hours is where you were at. Now, my scale is going to suck here because this is going to be kind of small. But, oops, I drew that very wrong anyway. Let me try that again. Make it a little better. There's 1,000 milliliters there. We are at 3 hours, we were at 850. Well, this is 800, so somewhere in here. At 5 hours, we were at 750, somewhere in here. Now, you said it right there. What'd you say, Josh? Yeah, it went down 100 milliliters in 2 hours. That's negative 50 milliliters per hour, or 50 milliliters per hour flow rate. From that, we know that our equation has to look like, come here, y equals negative 50 times x, if x is the hours. All we need to find now is where it started. This isn't going to be quite as simple. We know that there's going to be some number out here. The letter we use to represent the y-intercept is usually just the letter b. So I'm going to use the letter b there. To figure out how much this bag had in it to start, we can take either one of these points. This is 750, isn't it? So if x is 3 hours, y has to be 750 milliliters. Well, if we take negative 50 times 3 is negative 150. Solving for b, we would add 150. That should have been 850. Yes. Because it's 850, not 750 there. 850 plus 150 is 1,000 milliliters. So that's saying it started at 1,000. So the equation is y equals negative 50x plus 1,000. So we started at 1,000. If we want to know when it's going to hit 0, well, it's going to hit 0 when the volume is 0, right? When y is 0. You can solve that for y equals 0. Subtracting 1,000. Negative 1,000 equals negative 50x. Then what? Divide by negative 50. 20 equals x. So at hour 20, it is going to be empty. Well, like I said, you were probably able to figure that out thinking through it. You were going through these thought processes, just not formally writing them down. If you run, and part of it is because the numbers here were relatively simple. If you run into some, the numbers don't work out quite so prettily, you may have to write it down and work through it. But it's the same thought process. Like I said, there's a lot of things like this that I always showed in engineering that, oh, you write out the equation. I do them in my head because there's shortcuts to them, but the formal process is there. Okay, some homework for you guys to work on in the next week. Page 205 is just looking at graphs and reading graphs. There's only 3 problems there, 1 through 3. Page 213 through 217 is also more reading graphs. You want to look at 1 through 15, the odds. Page 221 through 222. 1 through 15, the odds. They're making some graphs. And then page 226, 1 through 15, the odds, is looking at more on slope and y-intercept and stuff. And we will talk more. Slope is really the big concept here. We'll talk a little bit more about slope next week. And then all the different relationships we have. Have a great weekend.